All right, good morning, everyone. So, just a recap from what we were looking at on Wednesday. On Wednesday, we were is just starting to describe the basic function of DC brushed motors, including in that the fact that you have um, basically two major components. I'd say three major components of a DC motor. Um, Let me zoom up here just a second. Okay, so you have the major components of a motor being the stator, the rotor. Right, so in terms of stator and rotor, stator, again, reminder, stator, the stationary part of the motor, the rotor being the rotating part of the motor, so that makes sense, right? And then each of these are going to either have, so the rotor almost always will have a electromagnet in it, especially for the brushed kind of DC motor. And the stator can have either permanent magnets in it or electromagnets. So either being coiled wire to make electromagnet or actually putting in the elements of a permanent magnet into the structure. And the other thing is the commutator, right? So this is the commutator is the electrical circuit that switches the direction of the current in the rotor as the rotor spins through its full revolution, right? So this usually happens on the order of somewhere on the order of 12 times in a rotation. That's about how many poles you would have on a standard DC motor. So, so what we then did after we kind of introduced those basic structures of a system is we talked about the torque you get from a DC motor, and we went through a little bit of math, and we got down to this expression that the torque is equal to the torque constant times the flux in the system that's coming from the stator, times then the current running through the circuit that is in the armature, or also called the rotor. All right, so this is K tau times phi being the flux times the current running through the armature. All right. And then I then discussed how this torque constant can be expressed in a variety of different ways. Usually if it's a field actuated DC motor, that means that we have an electromagnet which creates the magnetic flux that acts on the rotor. Then it's K tau times phi. If it's a permanent magnet, they usually lump then the torque constant and the phi together because that phi is constant. It's getting constant flux from the permanent magnets that are built into the system. And then we talked about the back EMF. So the back EMF, as a reminder, this is based off Faraday's law. This is the voltage that's created in a coil whenever time you have a rotating, something rotating through a magnetic field or moving through a magnetic field, right? And so we said this is given by Ka phi omega. So the main point here is that torque is proportional to current going through the armature. Back EMF is proportional to the velocity, or sorry, angular velocity of the rotor. Right? So the faster we spin our motor, the more back EMF we're going to get in terms of voltage generated by the system. And now today's lecture is basically going to go through some relationships and trying to understand that from the point of view of steady state analysis. Okay, so when we have a motor operating at constant speed, what would we expect to be the torque in the motor versus speed relationship? And then today we may start it, I'm not sure if we'll get there or not, but definitely by Monday we'll get heavy into dynamic equations of motion for motors, which everyone always loves that every year. So when we get to that, I'm going to have like a whole lecture where we're going to go through a multivariate linearization. So you're gonna think it's great. So, yes. So why is it included in the constants? Why is it not included in the constant? So I think that may become clear in a little bit that phi is going to be a function in time oftentimes. In the permanent magnet, in the case of permanent magnets, we're going to assume that the magnetic flux we get from a permanent magnet is constant. But if it's a field-generated magnetic field, so that means a field circuit-generated magnetic field. That means we have some sort of coil creating that magnetic field. That is going to be dependent on the voltage across the terminals of the motor, and we're going to assume that that's going to be changing in time all the time, especially when we get to dynamic analysis. Yes?
So like in physical terms, how does the back EMF affect like the motion of
perfect question to segue into this next. Yeah, one. So it's going to slow down the system, basically. So that's one of the fundamental limitations of motors and why they eventually slow down. And if you keep on cranking up the voltage after a certain point, they don't actually go much faster. Okay, so let's start to take a look at circuit representations of some sort of motor. And so what I'm going to draw here is a separately actuated or separately driven motor. So if you look at the book, this is a book from Rizzoni that's online, they give a variety of different architectures, and this is basically electrical circuit diagrams for motors. So you can buy a variety of different motors. There's really a few set ways in which they're wired up, and then that gives you the diagrams. We're going to only focus on 4 of those, and really only 2, and we're going to spend a lot of time on it. So the 4 of them are the separately actuated motor, which we're going to talk about first, and then we're going to have parallel series and also permanent magnet DC motors. Permanent magnet DC motors are the easiest to analyze because we have this source that's just creating a constant magnetic flux that you're assuming is not changing. Okay, so because for some reason there's a delay in my system today. This is going to be fun to work with. Okay, that's better. All right. Because of back EMF, the motor acts like a voltage source in the circuit. Okay, so I hope you appreciate this statement in the context when we talked about moving coil transducers, right? So the moving coil acts like a voltage source in that circuit. Same thing when Instructor Lake talked about generators on Wednesday, right? So that the element that's the back EMF in a generator is represented by a voltage source, and exactly the same thing here as well. So we're going to represent this as a voltage source. If this is a separately actuated circuit, and we'll get into the other ones in a second, that means we have 2 circuits that we can independently drive. So we have terminals for the field circuit. So this is the electromagnet in the stator, right? Which is going to have 2 terminals with it, and we can then drive a flux in this field. Electromagnet is composed of a bunch of wire, and so a bunch of wire has 2 elements that represent it. One is a resistance, right? So any length of wire is going to have a resistance associated with it. And I don't know if you ever wondered why an inductor has the symbol for an inductor has the shape of a coil. It's because there's a lot of analysis of transformers and also electromagnetic systems, which is in a coil form, and every time you have a coil, you have an inductance system because you have a long length of wire. So the inertia, the electrical inertia of that system is large. Right? So any type of coil is going to have resistance. We'll give RF, inductance LF, and then we can specify, or not specify, we can label the current going through this field circuit. All right, so the separately excited motor is the most general, really, because we can independently control what the field current is in the armature current. In the armature, so this would be the field or stator. In the armature or rotor, we have a pretty similar looking circuit. Again, we have terminals. This would be whatever you're actually connecting your voltage source to. This is again a coil, right? So it's going to have an inductance and a resistance associated with it. So given by RA and LA, respectively. And then the last thing, because this thing is turning and moving through a magnetic field, it's going to have a back EMF associated with it. And so oftentimes we'll draw that as some sort of voltage source. So voltage across the armature. We then also have a voltage from the back EMF. And let me move this up just a little bit, or move it to the other side maybe. And so oftentimes, if we want to denote that this is a motor, and it has a certain angular velocity associated with it, sometimes it makes sense to draw a motor shaft sticking out of it, and then you have a angular velocity, omega m. That would be just the angular velocity of the motor, m denoting motor. This would be a separately excited motor. Okay, so the whole purpose of this is just kind of give you the most general circuit diagram for a DC motor. And then we'll get into some specific forms in a second. So the reason why I say it's general is because this has two voltage sources with it, right? So you can have a voltage source for the armature or rotor, voltage source for the field or stator, right? So that's 4 terminals. Engineers sometimes like simplicity, and so there are a variety of different systems which can drive a motor with just 2 terminals. You lose some flexibility to independently change the voltage across independently change the voltage across your field and armature circuit. So we'll talk about 2 such versions of these. One is the shunt motor or parallel motor. So shunt motor or parallel motor. Okay, so it is called the parallel motor because the circuit for this is wired in parallel. All right, so everybody need to keep that straight. Pretty simple explanation, right? So we have a single voltage source. So given by V here. So positive terminal, negative terminal. And I'll start off by drawing the armature circuit because it's exactly the same as the case with the separately excited motor. So you have resistance of your armature, inductance of your armature, and then you have back EMF. So this looks, the mapping between here and here are almost identical, or they are identical. And then what we have, instead of having a completely independent circuit to drive the field, we're taking this voltage in parallel with the armature circuit. All right, what I'm about to draw here is a variable resistor. In case you've never seen the symbol, I'll walk through that in a second. Okay, and there's RF and LF. So just kind of mapping between the two. All right, so field circuit composed of a voltage source, right? And the separately excited with a resistor and inductor corresponding to the, basically the windings of the field coil. So instead of having this independently driven, we have a single voltage source that drives both of them. And the way in which we get flexibility here is we use what's called basically a variable resistor. So how many of you have seen a potentiometer before? Everyone? Okay, looks like maybe you had it in some sort of freshman engineering class, right? Okay, so potentiometer, if you were to rip apart a potentiometer and look at what's on the inside, you would have basically you have this strip, which is some sort of resistance to it, and then one end is then connected to a wire, and then the other end is this what's called a wiper, right? And this can rotate. And so if you rotate this more to the right, the length of the resistor gets longer, therefore the resistance increases. If you rotate it to the left, it decreases. Oh, sorry, then I mentioned this is connected to a wire as well, right? So this is just a way in which you're dialing or changing where you are touching this resistance strip, right? And so that's where this symbol comes from. So you have some sort of contact point, and then you can move this left or right to get higher or lower resistance. Okay, so what that does is it allows you to, with a single voltage source, voltage sources are fairly expensive. Variable resistors are pennies, okay? So it allows you, with a pretty inexpensive solution, to independently change the flux coming from the field with a really simple potentiometer and maintain a constant voltage if you want, right? So this is just saying this is a variable resistor, not the constant resistor you see in the CDC. That's the only thing that symbol means. Okay. So just to point out some things here, this is adjustable or variable resistor. Also, oftentimes called a potentiometer. All right. Trying to fit too much in a little space there. Potentiometer. Okay, any questions about the basic architecture? Yes?
Where does the potentiometer go on the motor? Is it like...
So you would see it kind of, well, so it wouldn't necessarily have to be in the motor. I guess what I'd say about this is that it would be somewhere where it's easily accessible to the user. So like a knob. So I don't know how when you used a potentiometer before, if it had a knob on the front of it, or if it was like sometimes it has a screwdriver slot, right? So depends on how the engineer built it, if it's a screwdriver slot or a knob, but it's somewhere accessible. Yes?
Does it generally use the actual windings as the places that the wiper goes against, or is it separate?
Yeah, it would be. Yes, the windings the windings in a motor are coated with this really thin polymer, so that it's electrically insulated. Right, so no, it's actually just be in series with it.
Okay, so it's like the actual field windings.
Yeah. Yeah. So it's not changing the number of coils; it's changing the resistance in that circuit, which then changes the current running through the coil. Right. So we remember that the flux is basically proportional to N times I. Right. So you're not changing N; you're changing I. So we're going to go through a steady state analysis on this. So steady state analysis, we just mean that constant voltage, constant load of the motor, therefore constant speed of the motor. We're trying to understand basic relationships before we get to dynamic relationships here. All right, so if we're talking about steady state analysis, really what we mean is dV dt is equal to 0, which then means if we then say what is the current running through the field, what is the current running through the armature, these are constant as well. And then we're going to have then the d omega, which is the change in angular velocity of this motor system. That's going to be constant as well. So what is the expression for voltage drop across an inductor? Do you remember? LdIdt, right? So if we look at voltage drop across an inductor, L di dt. Okay, so if we're looking at steady state analysis, we're saying that the change of current in the field, change of current in the armature with respect to time is equal to 0. And so in the steady state analysis, we're going to ignore the contributions from the inductors. These are almost like silent electrical elements in the system. Right, this is definitely not going to be the case when we get to dynamic analysis of motors, but for the case of steady state, there is no voltage drop across the coils from the inductance. There's a voltage drop definitely from the resistance of the coil. Okay, so if we look at this from a circuit analysis, we have two things. So we have the current running through the armature, right? So we want to express IA, right? We're really almost consider that this inductor doesn't exist. The current can be given by the current going through this RA resistor. So that would be then V minus EB over RA equals IA. All right, we'll look at Ohm's law for that element of the circuit. We have other relationships that we talked about on Wednesday, that we have the torque generated by the motor is given by K tau phi IA. Okay, so we're missing a few things here. We don't know what EB is yet. We don't know what phi is yet. But we could, if we were to get those, which we'll work on that in a second, we could get then the torque of this motor with respect to the voltage applied. Back EMF, also from Wednesday. Okay, related to the back EMF constant times the flux times the angular velocity of the motor. And then the last piece of information, actually we're going to hold off on that. So this is assuming that we know what the flux is. We'll talk about that in a little bit more detail later. We're saying we have a constant flux. We can now relate the torque to the voltage applied at the terminals. So if we want to now express everything in terms of torque, okay, so that's KT, or K tau phi IA. All right, IA is equal to V minus EB, Ka phi omega m, over then RA. Just putting everything together. All right, so that's the basic relationship. I think that's just kind of symbols on a page. I think the most interesting way to look at this is now to try and say, all right, what are the basic relationships here between speed of this motor and torque? Okay, from your experiences in maybe freshman engineering and other classes, at what speed is a motor the strongest? Did you go through that at all before we start plotting this? Sorry, you're pointing down. It's down. Lower RPMs, right? So the slower your motor is turning, right? The stronger it is, right? And that oftentimes, if you look at spec sheets of motors, you'll see stall torque, right? That's a very common specification. That's telling you how strong the motor is when it's at 0 speed, right? So it's a good metric to say, can you start something, right? All right. Is the load on the mechanical load on the system be so strong in terms of torque that I can or can't have the motor moving, right? Which is important if you ever want to get the system started, right? So for the series circuit, we have this relationship in terms of torque and speed, where we see omega m, and we have a negative omega m in terms of its sign out front. I forgot to mention it, but it's important to say that every single term you see here is positive, right? So all these coefficients are positive numbers. Right? So if we look at this relationship we can understand, all right, what is the torque that the motor is, what the motor can provide when the speed is 0. So if I look at omega m, right, so when the speed is 0, that means this whole second term doesn't exist, right? And so then my torque I can provide is at the level of k tau phi over Ra times then the voltage. All right. From here, the torque decreases linearly with the speed, right? Because it has a negative slope associated with the negative sign out front. So eventually you get to the no torque speed. And so basically your motor starts spinning so fast it is unable to generate any torque. This is the case, of course, in the no load condition. This is just a motor. I have it on my desk, put a voltage across. There's nothing actually slowing the system down. We're not even including damping in the system. And so if you then express or solve for when torque is equal to 0, you would then get k tau over Ka Ra times V. And then in between, we know this linearly decreases. That's a terrible linear line. Let's do it again. Slightly better. Okay, so we get this relationship. So the main thing to say here, this is just for the parallel or shunt motor. We'll look at a different form for the series motor in a second. But highest torque at low speed or 0 speed, linearly decreasing torque as we go up in speed. All right. So going back to the question about what does back EMF do, right? All right. So we didn't talk anything in this analysis. We didn't talk about damping on the motor at all, right? That's a mechanical system analysis. If we wanted to go into that, that would slow down the system as we go faster as well, right? Because the damping force is proportional to angular velocity. All right. So this is just the electrical circuit. The back EMF slows down this motor. Basically what it does is, if going back to my circuit diagram on the left-hand side here, all right, so this is a constant voltage, right? I haven't changed the voltage of this analysis at all. What we have changed is the motor speed, right? So if the high side of this back EMF increases because we're spinning faster, that means the voltage drop across this resistor is smaller. The current going through that resistor, therefore, is going to be smaller. So then the torque, which is proportional to current, becomes smaller. So it's an electrical limitation, and this exists in all motors. This is not unique to DC motors at all. Yes?
So that line, like linear fit, then not be, does that take into account the back EMF, or is that like just some, I don't know, idealization?
Yeah, so the back EMF is part of this equation. So that was this expression, where my cursor is here, which you then can see how that actually causes, when we solve for this, right, we have V minus EB, right? So that's where the negative sign is coming in. Yeah. It's a direct result of the back EMF. All right, yeah, so engineers, if you can figure out a way to get rid of back EMF in the motors, you're going to be richer than Jeff Bezos. So maybe that's an exaggeration, but I mean, this is a limitation that slows down everything that we see, right, in terms of automation, cars, etc. Oh, so other thing. Sorry, I forgot to mention this. So this is the relationship between omega and torque. It's also worthwhile looking at the relationship between voltage as well, right? So if we increase the voltage, V, what that's going to do is going to move this level set in this direction, right? If I decrease V, this is increasing V. If I decrease V, it's going to move this whole plot down in this direction. Right, this is going to just change the level sets. Yes?
Is peak power output at one of those two extremes, or is it
So
somewhere in the middle?
yeah, we'd have to. That's a different relationship. Yeah. So the question is about peak power, right? So power is torque times angular velocity. So if we wanted to look at peak power, we would have to basically look at P is equal to torque times omega m. All right, we'd have to analyze this a little bit more, but you see that torque has omega m in it already. So now we're multiplying by omega m, and also has a term that doesn't have omega m. So it's going to be some term that is quadratic and another term that's linear. We'd have to look at, have to take the derivative with respect to omega m to figure out what point that is. Peak power. Sure, why not? Let's do it. Okay, so if we have, so the question is what would the peak, the torque or the peak power versus omega look like? So P is equal to tau omega m, which that means that we're going to have k tau phi v minus ka phi omega m over Ra, all over Ra, times then omega m, right? So how do we find the peak of some sort of function, right? We take the derivative of that function and set it with respect to that function we care about and set it equal to 0, right? So d power d omega m is going to be equal to then k tau phi over Ra times v minus then it would be 2 k tau phi ka phi omega m, 2 phi's in there, right, over Ra. So then you're asking, okay, what would be the peak power speed, right? We'd have to solve this then for 0. Please be checking my math as we're going through here. So we have this RA cancels, this phi, one of these phi's cancel, okay, tau cancels, right? And so then you get V over 2 Ka phi equals omega m, we'll call this peak. As first pass. Did I mess up something? Where are you asking about the phi squared? I distributed k tau phi to the right hand. So just so let me walk through this. So if I were to expand this out, right, I have k tau phi v over Ra omega m. That then becomes this term. I take the derivative with respect to omega m, so then I just get k tau phi v over Ra. All right, second term, k tau phi ka phi again, omega m squared over Ra. So that means I have k tau phi squared ka, and then I had omega m squared. I take the derivative with respect to omega m, so it gives me 2 omega m, right, over Ra. I think it's correct. I have to double check it. Yes. Yeah, one of them canceled it. Yeah.
So I follow what you did, but at the same time, like if you look at the torque versus omega plot, since it's like a linear line, I would have thought that it was linearly proportional. As torque goes, you know what I'm saying?
Yeah.
So then if you just torque
Yeah.
times the speed, then it would just be constant the whole.
Yeah. So the relation between torque and speed is linear, right? But the expression for power is torque times speed again. So you now get an omega m squared term in there.
Okay. Thinking about it wrong.
Does that make sense though?
Yeah.
Okay. So that's steady-state analysis for a shunt motor or parallel motor. We can do the same thing for series motors. So series motors. Okay, so series motors are, I think, as the name suggests, is just the same idea. Really doesn't really differ in actual physical hardware you build into this, but you wire up the circuit differently. All right. So instead of having a field circuit and armature circuit that are in parallel, I think, as the name suggests, you can guess it's going to have V in series. Or sorry, the two circuits in series. So we're going to have inductor coil, LF. Oftentimes you won't see the resistance for the inductor or for the field and armature circuit separated out, because from a dynamic analysis it doesn't matter. You would just see a single R, and this lumps together the resistance of the armature and field circuits all in one. LA, and then of course you're going to have back EMF. I, and then we have back EMF. Okay. So some things to keep in mind here is that the before on the parallel circuit, going back to that diagram, okay, so the current running through the field circuit never changes, right, at steady state. And that's because the voltage never changes, therefore the current running through the field circuit never changes, therefore phi never changes. This is definitely not the case with the series circuit. As the back EMF gets larger, that means then that the voltage is the high side of the back EMF increases. That means then the current running through the field circuit changes as well. And so when we analyze series circuits, we express this flux as a function of the current running through the field. So in this case, we have a single current running through the entire circuit I, so we don't have an independent current or field current. And so then we say that this flux is a constant proportion of then the current running through the field circuit. So taking this back to what we learned with, say, solenoids moving iron transducers, we said that the flux is proportional to the number of coils times I. Same idea here. This is a constant proportion, right? So the flux coming from your motor is determined by some sort of constant times the current running through that coil. Yes? Sorry?
Can you not add the inductors?
You can, because it's a dynamic relationship. Yeah. All right. So similar relationships here, or similar statements that we can make. We have torque. So almost exactly as we had before is k tau phi I, right? But phi is now a function of I as well. So if we now put all these together, we get k tau, ks, I squared. Right. Voltage, okay, using Ohm's law, voltage is equal to basically the so VA, which is the total drop across here, is equal to the actually, sorry, this is using Kirchhoff's voltage law. If we look at this voltage drop, or this is a voltage increase going from negative terminal to positive terminal, that's equal then to the drops in voltage. So then we have a drop in voltage from the current running through the resistor, and then another drop in voltage going across the back EMF, Ka phi omega m. All right, we have expressions for phi, so we can now write everything in terms of I, Ka, Ks, omega m, plus R, I. And then we can throw this all together, and then we get the torque as a function of omega again. Okay, so a little bit more complicated relationship mathematically. So easier system to analyze in terms of just looking at the elements because it's all in series. Mathematically, it becomes a little bit more difficult to look at. Yes? This is only for steady state. And I, just before I forget this, I missed a parentheses. Yep, only for steady state. Okay, so again, the question when we talk about parallel circuits, parallel motors, at what speed is the motor going to have the most torque? Same is true here as well. So if we look at the case where omega is equal to 0, that makes the denominator the smallest it can possibly be. All right. Here. Okay, so we have then this relationship. Okay. Sorry, we can't see the expression right now, but the highest possible torque you can get would be K tau, Ks, Vs squared over R squared. And then if we look at this expression, it's asymptotic in omega m, right? And it's asymptotic with respect to omega m squared, the denominator. So it's going to have this form where it then asymptotically decays to 0. So it never quite reaches 0, unlike the parallel motor, but it's just going to continue to just get lower and lower as speed goes up. Again, the reason being back EMF. Right. Kills all the fun. Right. Other relationships, as V increases, as you can see here, that's going to just shift this entire plot up. So this is V going up, V going down, shifts the entire plot down. Yeah. Yeah, so you want to get to the equation, right? That's what you want. Okay. Zoom out. Yes, Carson.
So for all motors, is maximum torque installed?
There may be some really strange motor out there that I'm not aware of that does not have this property, but yes, in general, that's true. Yeah. I won't say like without bounds that this is not true, but it's for every practical motor, yes, that's the case. Okay. All right. So in the last, okay. Which one? Oh, Ka. Is K. It's a good question. I should know that, right? That's an A. Okay. So that's That's going from the back EMF constant. So the back EMF is equal to Ka B omega. Okay, so I'm not going to spend much time on permanent magnet motors, not because they're not important. They quite are. They actually are very important. You're seeing more and more permanent magnet DC motors because of a lot of applications where they care about having lightweight motors, and so you can get, and also you can get really good permanent magnet motors anymore in terms of better permanent magnet sources. So these are becoming more and more popular. They're more pricey usually, but still very, very useful. I'm not going to go through this one because it's considerably more simple. The flux is constant. It's not a function of the voltage applied. And it's a pretty simple analysis. And we have to move on to dynamic relationships for these motors. Yes. Yes?
Does the permanent magnet on the motor like lose its magnetic like property over time? Or
Yeah.
it seems like you're getting like free. Like it takes energy to make the field.
Yeah.
And the other motors we talked about, then you just get like a free field
Yeah.
permanently.
It's like free lunch, right?
Yeah.
Yeah. Yeah, so yes, it will lose over time, especially as it's sensitive to thermal cycling is one thing, and other, you can actually demagnetize it. So I would say that it's not necessarily free. The reason why it's magnetized is it has either a lot of energy put into it at the factory, right, or the Earth put a lot of energy into it at one point in time. So it's not exactly free. There was something put into it a long time ago that gives you the ability to continually generate a magnetic flux. Okay. But you can thermally cycle them and break down the flux in them, and then it'd be very expensive to ever regain that. Yeah, so there are some sensitivities to that. I will say though that they're used all over the place with a really high reliability. Okay, so a lot of hybrid vehicles have permanent magnet DC motors in them. Or other types of asynchronous AC motors that are built on permanent magnets. The Tesla 3 has a permanent magnet motor in it, not the Tesla S, but the Tesla 3 does. So they're in a lot of cases where you want really high reliability. Right, so they're pretty reliable systems. All right. Okay, so that actually, sorry, I forgot that's a really good segue to the next kind of statements. So, PM motors are lighter, smaller, and more efficient. So just a note, Instructor Lake, who brought in recitation a permanent magnet motor and showed you it running and also showed you the back EMF from it. So that was a permanent magnet motor we bought because we wanted to have a lot of torque in a pretty small package. We didn't want to have this bulky coil that's on it, right? And so we spent the extra money to get one of those. That motor that we then, I subsequently fried and caused it to smoke, cost $500, that little thing. So yeah, they're really expensive, but they're also, if you want something that's really lightweight and really powerful, you get a permanent magnet motor. Yes?
How much voltage could she have put to that? Because like she was just kind of keeping it really low for the demonstration.
Well, it's already busted, so she couldn't have hurt it, I guess, besides causing a fire, I guess. I don't know. So it's rated, that motor's rated for 24 volts. Okay. Now, when I caused this thing to smoke, I obviously exceeded one of those limits, right? So I sent too much, I had a current supply and I sent too much current through it. So it's rated for, I believe, 24 volts and 1.5 amps, and I must have went over 1.5 amps. So anyhow, so what it does, and I talked about this a little bit, there's this insulation on the coils, that keep all the coils separate, and then it gets so hot that it starts to burn off the insulation, and then you get short circuits now. And so instead of having 100 coils, some of those are shorted now, so maybe you have 50, right? So then your motor becomes weaker. Yes?
Is it possible to exceed the current limit of a motor but still be within the acceptable voltage range?
Not really, yeah. So I guess maybe I must have exceeded the voltage range too then. Yeah, I must have. I don't know, I wasn't monitoring the current or the voltage, which is part of the problem. So, yeah. So expensive mistake. All right. Has linear speed torque relationships. That's not too important. The question was about demagnetization. Be demagnetized by excessive magnetic fields, excessive voltage, extreme temperatures. And also noted, as it's stated in the book, they have greater variability. Okay, and this is because the permanent magnet source can have some variability in it. It's from the Earth, essentially, right? So it's going to have variability. The other thing that is worth mentioning, it's not in the book, but it's just some things I read and reasons why people are making certain engineering decisions about this. So when Tesla wanted to build the Model S, they went with an inductor. They went with an asynchronous induction motor. And the reason, and we'll get into induction motors just briefly in this class, the reason why they went from that is it can be made purely out of copper. And then sources that can be, materials that can be sourced within the United States. There's some issues with some rare earth elements and where we're getting them from and whether or not there would be political conflicts where we would continue to get them. Okay. So rare earth permanent magnets, we don't have a really good domestic source, so you have to get them internationally. And some countries want to just shut down the supply. A lot of U.S. companies would have to really figure out how they're going to make motors if they don't have permanent magnets anymore. So that's another kind of aside as well. Okay. Actually, I only have 2 minutes left, so I think it doesn't make sense to jump into a really big subject next. So any questions in the last 2 minutes about what we talked about today? Okay. Oh, sorry. Go ahead. Why the flux is like?
It's not constant for series motor.
Okay, yeah, let's talk about that. So let's compare circuit diagrams here. Okay, so I think the easiest one to explain is starting with the parallel motor. So with all of this, we're talking about constant voltage, right? And so we're looking at the relationship between torque and motor speed, right? So motor speed is a function of many things. One being the torque applied to the motor, but it's also the load torque, whatever this thing is driving, right? So if it's driving like a little tiny wheel on your desk that doesn't have much of a resistance torque to it, not too much of a load torque. If it's driving a car, pretty large load torque, right? So it's going to be very dependent on the load torque. So we're looking at relationship between voltage, which we're saying we're hold constant, and torque, and speed. Sorry, look at the relationship between torque and speed, right? Now, if we look at the circuit for the fields here, nowhere in here is the current running through the field dependent on the back EMF, which is proportional to the speed of the motor, right? Because the current is just dependent on the voltage and this resistor value. That's it, right? If we look at the series motor, it's a different scenario in that this current running through the field, given here, right, is dependent on the back EMF because it's wired up in series instead. All right, so this voltage drop, which determines I, is going to be dependent on back EMF. Make sense? Okay. Yes.
For the permanent magnet, what do you mean by greater variability?
Yeah. So if we have copper and we're making coils, we can count how many coils we're going to make, and we're going to get approximately the same field strength every time. Variability would be you're now making permanent magnets from rare earth elements, and that's coming from the earth, and the manufacturing processes are such they don't have as much control over that. And so you buy motor A and motor B, same exact make and model, right, but you'd have different flux in each of them. All right, have a nice weekend, everyone.